Good morning. Good morning, everyone. Now we are at the end of this marathon on shot peening. Okay, let's start the last day. Okay, no problem. Okay. Last day, indeed. Today we are starting with an additional part about, indeed, shot peening for additive manufacturing. Indeed, the subject I'm talking briefly now today, starting the morning, is not only for application dedicated to additive manufacturing, but also for traditional shot peening on traditional material. But anyway, this is of particular interest for additive manufacturing. And indeed, we have called gradient shot peening. It is a novel way, let's say, nothing breakthrough, but anyway, a novel way to apply shot peening, and especially to apply air, air shot peening. That is to say, when we are using compressed air to accelerate the shot. Why? Because indeed, when the usual way shot peening, air shot peening is applied is to set up the pressure of the air and then maintain it constant for the entire duration of the treatment, let's say, according to the result of the internal element intensity we want to achieve and that we have fixed by setting up the parameters. Okay, and the final result is this in this. Indeed, the final result is associated to the total duration of the treatment, and we see what's happening step by step. If we have a duration equal to, let's say, t here, we will have a number of dimples of indentation here. If we double the time, the number of indentation will cover a larger area of the impact surface, and that's all. Okay, this is indeed, and the same we can see indeed. If you are using larger intensity, indeed, the indentation will be larger, and finally, we will need less, let's say, less shot, less impact to have the complete coverage. And at the same time, indeed, we see that the number, if we increase in the intensity of the treatment, and indeed, the indentation depth and dimension will increase. Okay, and the way air shot peening is done is using a regulator and a valve. Okay, the projection of pressure of shot peening process is controlled and is regulated the velocity. Okay, and finally we obtain the effect we already know, that is surface roughness and grain refinement close to the surface, an increment of the hardness, and then finally also or for the residual stresses under the surface. Okay, and this is the usual way. Let's see. And indeed, I have defined in the last day severe shot peening as the treatment, of the shot peening treatment that is able to induce, to emphasize, let's say, the effect of the shot peening in terms of microstructural grain refinement. Okay, and but we also notice that indeed, at least if we are using a higher intensity, we can reduce the time, but finally we risk to damage the surface because the impact energy is too much. And step by step, dimple by dimple, indentation by indentation, we can go in the so-called overpeening that is not wanted, but is damaging the surface. So how can we consider that this different way to perform shot peening? We can draw a graph where we can put the time, the exposure time in the abscissa, and the projection pressure in the ordinate. And this is dedicated to air compressed shot peening, pneumatic shot peening, of course. And we see that we can have different different region, let's say, they define a different way to apply shot peening. What we call CSP, that is conventional shot peening, is something that is here in the green area. That is to say, usually 100% is the coverage, sometimes 200%, but no more. And the Almen intensity is something that varies with the material. Of course, the usual Almen intensity is varying with the material. But anyway, is not exaggerated. The Almen intensity is always, let's say, is included in this region. And when we apply conventional shot peening, we are covering one point in this area. What's happening if we apply severe shot peening? It means I said that we are applying or a larger Almen intensity or a longer exposure time. Okay, and indeed, I did not say it's written here. The exposure time is related to the surface coverage, we say, and the projection pressure, the pressure of the air, the compressed air, is related to the value of the Almen intensity. Okay, if we increase the pressure, we increase the Almen intensity. If we increase the time, the coverage will be 200, 300, 400%, and so on. Okay, what's happening if we increase Almen intensity and or the surface coverage? As said in the last day that we are obtaining more effective macrostructural modification in the surface layer of material. Okay, we are obtaining the grain refinement if even to nanoscale, to nano-level scale. Okay, and we can indeed qualitatively define the area of severe shot peening as the orange area. And we can go this way, indeed. I said in the last day, the first attempt were done by my group by considering higher Almen intensity and also a longer exposure time, something like this. We consider a larger Almen intensity than with respect of the usual value, and then we prolong the time along this line. Or another way, and that we are doing, we did later, is to consider usual Almen intensity value, but prolong the treatment much more. The exposure time is much more, so the coverage is 800, 1000, and so on. Okay? And which is the problem? The problem is that also the severe shot peening region is not unlimited. If we exaggerate both with the time or with the Almen intensity, it means that we will go in the over shot peening zone. The red one here that that define the zone of the treatment, is the values of the coverage and the Almen intensity that are causing surface damage. So if we are in the red area, we are not obtaining indeed an advantage anymore, but we are decreasing the final performance. Initially, we are decreasing with respect of a maximum, let's say, and then if we exaggerate and proceed, finally we will also cause a premature failure, also with respect of the unpeened sample. Okay, this is the usual way we perform or conventional shot peening or severe shot peening, and taking care not to go in the overpeening area. And this is the boundary. Indeed, here the boundary is clearly defined, is aligned, but anyway, in the practical application can be more can be not so well defined, and could be also difficult to assess during the design of the treatment if we are severely peening or overpeening the part. Okay. Okay, this is done. And let's say what we have done. Okay, first of all, and this is the theoretical. Now let's see what. Okay, they are synchronized now. What we have done and what is gradient shot peening. We have applied this treatment, the new way that I'm going to present now, to the alloy silicon-10 magnesium. The sample, hourglass samples is like this, obtained by using laser powder bed fusion. The sample were also treated and then shot peen. And then let's see what is shot peening, what is severe shot peening, sorry, gradient shot peening, before defining the parameter we have used. You already know, at least partially, this figure. Indeed, here we are representing the different effects induced by shot peening. Here you see what we have done, the shot peening treatment. Here you see the other graph that I have just commented, where the different zones that define CSP, conventional shot peening, severe shot peening and over peening are drawn. Okay, and indeed, considering that severe shot peening is good, is going to obtain better performance with respect to conventional shot peening, but at the same time we are losing some of the advantages due to the surface roughness, we must think to something that is able possibly to reduce this effect. And maybe is able to sometimes to avoid, or anyway to make not, in some application, not needed, not necessary, the need of a final electrochemical polishing process that we commented yesterday. And the idea is this. Here is the same graph, and this is peening duration, time. Here is the pressure, projection pressure, so the Almen intensity, let's say. Here is the zone of CSP, and then SSP are here. The idea is this, is to apply shot peening not with a constant pressure, air pressure, but to perform shot peening increasing during the treatment the pressure itself. So starting from low value, typical of conventional shot peening, and then step by step during the treatment going upper to an upper value of the pressure. So something that is able to increase instantaneously the Almen's intensity we are applying. What is the idea behind? And in this way, we maintain the maximum value of pressure. So we can get the same residual stresses and the same microstructural modification. At the same time, the reduced number of impact at the maximum energy should be able to reduce the roughness. And so finally, we could have even a better benefit than severe shot peening, the severe shot peening. And we have indeed, we can decide to vary the pressure during the treatment as a function of time, let's say, in different way. Here, indeed, is linearly value in the blue line, this is continuously increasing from the minimum to maximum value. In the other option, that is this, we are increasing and then decreasing. So we reach the maximum at 1/2 of the total time, and then we decrease, and the treatment is concluded when the pressure is equal to the initial one, very low. Okay? And we investigated these two cases, and we call this possible way to apply shot peening, where the pressure is varying with time, as gradient shot peening. And in this presentation, I call ascending severe shot peening, ASSP, the treatment where the pressure is continuously increasing from the minimum to the maximum value, and AD-SSP, ascending descending shot peening, the treatment where the pressure is go up and then down at the end of the treatment. And the idea is to compare which is the treatment between ascending shot peening and ascending descending shot peening that give the best surface result, and finally the best fatigue result. Okay? And the idea is this, is to maintain, let's say, to maintain the other effect of severe shot peening, that is to close the pore, to induce residual stresses, increase the hardness the hardness of the material and obtain a gradient nanostructure from nanograins to ultra-fine grains and then to the core in such a way that the fatigue limit is improved more than with the other peening parameters such as severe shot peening used with the same parameter. This is the experimental activity. This is quite similar to what I showed yesterday, talking about the smooth sample obtained by LPBF. Okay, this is indeed the construction is the same, so the parameter of the laser machine are the same, 350 watts is the power and so on. And each layer was obtained by rotating 67 degrees with respect of the previous one, and the building direction is the same as the axial direction of the hourglass sample. Okay. Then we perform a T60 treatment, the same we performed yesterday. Finally, a shot peening parameter. And here the treatment we did are more quantified. Indeed, the shot peening was performed on this sample, on the central part of this sample. The time was from 0 to 300 seconds, so this is the duration of the treatment. And in 300 seconds, we have 3 different treatments. One is indeed conventional shot peening, then that is this, we cannot see in the slide. Ascending shot, severe shot peening is this, where we stop here at 1/2 of the total duration. Overshot peening, we use the same pressure of severe shot peening, but we prolong the treatment much more till the end, till 300 seconds, to induce damage. And then we consider ASP, where the pressure goes from the 1.5 bar to around 3.5 at the end of the test, after 300 seconds, and ascending descending, where we go from 1.5, 3.5 at 1/2 of the treatment, so 150 seconds, and then back to 1.5. Okay? These are the shot peening parameters that we consider for these 5 different ways to apply shot peening. The diameter of the shot is the same. The shots were always the same. The projection pressure is 3.4 for conventional, severe, and overshot peening, the same. What is varying is the coverage. For conventional shot peening is 100%. As for SSP is 10 times larger, so 1000%, and for overshot peening is 20 times larger, 200%. Okay? And the Allman intensity is the same for these 3 treatments. So the difference is related to the coverage. If we consider ASSP, so ascending shot peening, the blue line here, the pressure is changed from 1.4 to 3.5. The Allman intensity is going from 7 to 14, and the duration is 300 seconds. Okay? It's not indeed, due to the fact that the pressure is varying, indeed, it's not possible to define really a coverage. But anyway, it's important that the duration is clear. And for ascending descending, we have a similar trend, but the pressure go up from 1.4 to 3.4, and then back to 1.4, and the Allman intensity is 7, 14, 7. Indeed, we have already, these are the microstructural observation in the as-built and heat-treated states, so before shot peening, and so these are similar. We can do the same comment we did for yesterday, that the effect of heat treatment in making much more uniform the microstructure, removing the typical patch of the caused by the laser beam. Here again, some other microstructural observation of the treated sample by MIME SSP and the other treatment that via EBSD. Yeah, it's a pity at the screen it's not possible to clearly recognize the figure, but anyway, we see here that we have ascending short peening, ascending descending short peening, and each of them correspond indeed to an almost similar level of grain refinement. Here are the hardness and residual stress measurements. In the left part of the slide, we have the hardness. Oh, sorry. Here we are in the left part of the slide, A and C, we have the hardness and residual stress without the treatment. Here we have the same quantities for the sample that were heat-treated and then shot peen. And what can we notice here? We can notice indeed the different effect of each shot peen heat treatment, okay, and the difference with respect of the S-built condition, that is the lower curve here for hardness, for instance. And we see here that indeed, in terms of hardness, overshot peening reach the peaks here, and the curve is the more invasive treatment, let's say, with the larger surface and in terms of depth is not varying so much with respect of the other one, but is the more invasive. While if we compare conventional shot peening and the other shot peening treatment, indeed, we can notice a difference by increasing the severity, let's say, of the treatment. At the same time, we can notice that by considering ASSP and ADSSP, that are the treatment we are interested in this study, we see that the result is similar to what we can get by means of SSP. Okay, in terms of residual stresses, similar comment can be done. Indeed, the strong effect of every shot peening treatment is observed with respect of the S-built material. And at the same time, what can we see is that if we are considering the overshot peening, okay, and severe shot peening, indeed, and we compare them with AASP or ADSSP, indeed, the trend of residual is almost the same. So it's true that with this pressure gradient with time, with pressure application, pressure variation, let's say, with time, we are not losing anything about with regard of micro hardness and with respect of residual stresses. And the same comment can be maintained with different values, of course, after if we perform any treatment before the shot peening treatment. Okay. Here are the results in terms of porosity. And what can we see here? The porosity is larger in the S-built condition. If we apply conventional shot peening, there is an effect, but not very remarkable, let's say. The effect is much larger if you consider more severe treatment. SSP, overshot peening is able to reduce porosity even more, okay, because it's the CV needed larger intensity and longer time. So it's, but it's too much. Let's see then how it goes with the fatigue strength. And indeed, ASP and ADSSP are also able to remove to reduce the porosity in a positive way. Let's say we are around from 0.6, we go down to 0.4. That is similar to severe shot peening. And the same after, if you consider the treatment performed after the process and before shot peening, the similar comment can be done. Okay, and another interesting thing to be observed is the distance of pores that are close, the distance from the surface. Okay, and it's quite short if we refer to, if quite short, good choice. We refer to AB plus CSP, and then indeed, and the effect of ASP and ADASP is still notices, with and without the treatment. Okay, now let's see the roughness. This is maybe the most interesting parameter to consider, because it's what we want by means of this gradient shot peening. This is what we want to change with respect of the other peening processes. What can we see here? That the as-built condition is considered as the reference case. Okay, the blue and green line bars represent RA and RQ. And these are indeed, in the as-built condition, we have 9 RA and 12 RQ. After conventional shot peening, we are able to reduce this value to 6 and 8. Severe shot peening is better than as-built, but anyway, able to induce larger roughness, and even more if you consider overshot peening. In this case, we are not improving at all with respect of the as-built condition. It's interesting to notice that by means of AASP and ADSSP, we are reducing the roughness. In particular, if you consider ascending-descending, the roughness is even less than the one we have obtained with conventional shot peening. So, by means of gradient shot peening, we are able to maintain the same level of residual stress, maintain the same level of grain refinement, microstructural modification, let's say, and at the same time to get a better surface roughness with respect of also of the conventional treatment. Okay, and the same can be said and is confirmed if we consider the heat treatment, the T6 heat treatment performed before shot peening. And here there are some images taken at the SEM or the confocal that describe the morphology, let's say, of the surface after this different treatment. So let's go to fatigue now, the fatigue strength. And this is what is more interesting to comment from a practical point of view, let's say. What can we see? That in the as-built condition, also in this case, as we did, yes, as we commented, yes, we have considered, due to the limited number of samples, we have considered one stress amplitude, okay, for all the treatment, and 3 samples each treatment, okay? And then you see here the result of the 3 samples and then the average. But we can see that the final result is uniform. Indeed, the scatter between the difference of the number of cycles of the 3 samples is not huge. They are almost aligned. And we see that in the as-built condition, the fatigue strength is quite poor, and each of the peening treatment is able to greatly improve the fatigue strength. Conventional shot peening, severe shot peening a bit more. If we are considering overshot peening, it's true that we are going to damage the material because we start decreasing the benefit. So we have reached a maximum, let's say, with severe shot peening, and then increasing the time we are damaging the surface. If we increase the treatment even more, the result will be even worse, of course. And what is interesting is to see is that with ascending, descending, or even more, ascending shot peening, or even more with AD, SSP, ascending, descending shot peening, the fatigue strength, the result is the best. So by means of this treatment, this way, the new way, let's say, novel way to apply shot peening, we are able to get the best result. And this is also confirmed by the test performed on the sample that were also subjected to the thermal treatment. In the graph in the right side of the slide, we can see the fatigue life improvement compared to the S-built state, so in percentage, and what indeed. And what can we see that also in this case we see that ascending descending is the treatment that is able to give the best result. So what does it mean? That if we consider shot peening, we consider some new way to apply shot peening, we can even improve the surface morphology, surface roughness, and make the treatment even more effective with respect of the usual way we apply shot peening. Okay, and this is of particular interest for additive manufacturing part, than what we have done. But we have also considered some tests on traditional material, let's say, and the same conclusion can be drawn. Okay, and if we are able to, indeed, now these are the first experiment with this gradient shot peening, but we could also try different pressure time law, parabolic maybe, and indeed, and we are adding a variable to the process, and so this makes also the definition of the optimal conditions even more complicated, and maybe in this case an approach base that includes also machine learning is even more useful, even more, okay. And in this way we are able, but anyway, in this way maybe we are able to avoid the final finishing surface, the final finishing surface treatment, that is surface finishing treatment, that is to say, to avoid the polishing, for instance, could be not necessary, and so we are removing one step to the final process of additive manufacturing. These are the fracture surface. See here, and we can see here. Here is it can be noticed the crack initiation point, and we see we have AB is the first line. AB is this. AB plus CP is here, and the other treatment SSP over peening and ASSP and ADSSP. And we see that the point of crack initiation is different. In particular, what can we say? That in the S-built condition and the over-peened sample, the fatigue crack starts from the free surface. So the improvement that we have obtained on the surface is not able to prevent crack initiation. In the other cases, that is conventional shot peening, severe shot peening, and the gradient shot peening treatments, we are able to shift the crack initiation point from the surface to an inner point. And this is what makes the disability, is what makes this treatment more effective than the other one. Okay, we are far from having optimized the gradient shot peening, but the results are quite interesting and encouraging. Okay. Any question?
Can you please kindly comment on that?
Sorry?
That has built fatigue life, sir. That fatigue life.
Yeah.
Yeah, here, the third green one, the as-built plus heat treatment has the lowest fatigue life improvement of 3%. The green one, sir.
This one?
Yes, sir.
Yes.
Yeah. Please comment on that, sir.
This is indeed, in this case, we have not analyzed the problem in detail, but anyway, we think that the reason is that the treatment is reducing in this case, reducing the mechanical property, the yield stress and the UTS, but is not able to induce, in this case, pore closure, or some defect remain, and so in this case, the basic microstructure remain the same, okay, in terms of mechanical improvement. And And due to the fact that with the heat treatment, we are reducing the yield stress and the UTS, finally we have a ROS, lower number of cycles to failure.
Thank you, sir.
You're welcome.
Sir, even in this CSP or conventional short peening, don't you think there is a gradient effect? Because at the top surface you have high compressive residual stresses, and as we move on to the depth of the workpiece, slowly it is turning out to be tensile. So there is, I mean, is there not a gradient effect in CSP as well?
Is there an effect of?
Is there not a gradient effect in CSP as well? Because from high compressive residual stress on the top surface, and as we move to the depth, the residual stresses, compressive stresses turn out to be tensile. So there is a gradient effect in CSP as well, right, sir?
In terms of residual stress, yes, but to which gradient effect are you,
No, sir,
referring
I'm
to?
just trying to compare CSP or conventional short peening and gradient short peening.
Okay.
So in both cases, let's first consider CSP or conventional short peening. In that you are applying certain intensity, say X intensity, Alman intensity.
Conventional is 100% coverage, the minimum requested for covering the complete surface. Okay? This is CSP.
Yes, but then, you know, in CSP we have high compressive stress on the top surface, if I am not wrong.
Let's see. We can. Here. Okay, so this CSP is this.
Okay.
Okay? And you are comparing with gradient shot peening, that is the green and gray that are here. Okay? So the surface residual stress is different, but not very different. What is more, then the curves are diverging, and for the gradient shot peening is going deeper.
So my clarification is like, even in conventional short peening, there is a slight gradient difference is there. A gradient flow is there actually, if I'm not wrong.
For residual stresses, you
Yes,
mean?
yes.
Yes, sure. It's not constant. But here, we call gradient not referring to residual stresses, but referring to the pressure
Right.
application.
Pressure
The
application.
pressure is not constant, but is varying with an assigned gradient.
Okay.
This is and ascending descent means that we are increasing, the gradient is positive or negative, and we are going up and then down.
So that gradient effect is solely limited to that applying Alman, the intensity.
The gradient is referred to the pressure time variation. Okay. And the final effect, what we want by means of this new way to apply shot peening is to improve the surface quality, maintaining longer time, and so maintaining grain refinement.
Sir, in one of your work, the modeling of fatigue behavior via machine learning, sir.
Yes. So,
Sir, how many data points are used to developing prediction model, sir?
how many?
Data points, sir. How many?
I don't know the number. It was a huge number, but indeed, I have not in mind the number of points, data point we have used. Okay.
Okay.
I can write you but this is for sure my PhD know better than me. They have done that. But anyway, it was I did them this question. They convinced me that there was a huge number of parameters, and each parameter with the training was quite accurate. Let's say. Okay.
Yes.
Okay, I think we can pass to the next presentation now. That is the other processes. That is shorter, so we should be able to finish for the break. What I'm talking about now. Indeed, I'm introducing the other most common peening treatment. Okay, that are used. Indeed, we have already introduced some of them, talking about fatigue alleviation method, just in terms of effect. And now I will spend some more work, okay, to to see and to distinguish this treatment with respect of shot peening in terms of practical application, and at the same time to see which is the final result and how can be similar or not similar to what we can obtain by shot peening. Let's start. These are the list of the treatment we are considering. This is the outline. So let's start from strain peening and worm peening. In the stress peening, we have already commented more than once during this course. What is this? In the strain peening, or also called stress peening sometimes, is shot peening applied when also a mechanical load is contemporarily applied. Okay, and we have mentioned the classical example of the leaf spring, where the leaf spring are usually shot peen on one side, okay, but because they have a unique direction of the load. This is from ground to bottom up, okay, this way, and the most critical part is the part that is into that the leaf spring is bent, of course, is in bending for the load application, and part of the beam of the that is in tension is the upper part. So we need to pin especially the upper part because the crack will start from that point. And how can we improve the effectiveness of shot peening? If you apply shot peening while we are applying a load that put in bending the upper part of the spring, finally the residual stress will be larger. We are considering to apply residual stress on a part that is under tension, and this makes possible to induce harder residual stresses. Of course, a treatment like this is useful for pulsating fatigue cases. That is to say, when the load is just in one direction. In this case, the load goes to 0 to 10 kilonewton or something, and goes 0, 10 kilonewton. It's never going minus 10 kilonewton. The minimum load is 0 and the maximum is defined. Okay, otherwise, what's happened? Otherwise, it's happened that if the load is alternate, let's say, and change the sign, the part that is under tension will become in compression, and the part in compression will become in tension. And if we are applying stress peening, the part that is in compression will be affected by tensile residual stresses. It's okay if it is remain always in compression. If you have a load that makes this part in tension, this will cause a premature fatigue failure. Okay? And the tuning, the design of the preload is an important factor to have the best result. And this can be predicted, let's say, assessed by means of also numerical simulations. What is more peening? I was discussing with some of you yesterday. Indeed, more peening is another way to perform shot peening. It is, indeed, it was developed some years ago, and then to my best knowledge, no one is investigating on this. The idea is this, and it is used especially for carburized material, for gears steel, let's say. The idea is this, that by performing shot peening at a temperature of 300 degrees, okay, we are able to induce at least in this kind of steel, a more favorable residual stress. We are able to increase the residual stress. Okay. The reason why, indeed, is there is some microstructural factor, but the reason why is not being really clarified, indeed. And you see here the different result in terms of residual stress that can be obtained by means of the different treatment. So if you apply shot peening at 20 degrees, we have this trend. If you apply the shot peening at 20 degrees plus stress gradient that goes, and it is that we maintain the sample at 300 degrees for 20 minutes, the trend is decreasing. But if we apply shot peening with a temperature that is to around 300 Celsius degree, the profile is a bit better. And finally, what can we see? That the best fatigue results are obtained by means of the latter treatment. That is, if shot peening is applied at 290 degree, Celsius degree, the fatigue limit is improved of around 20% with respect of the other treatment, of the conventional shot peening performed at 20 Celsius degree. And anyway, each of these treatment have an improvement with respect of the ground material. That is the lower curve. Okay. Why it was no more, maybe someone is using, but why it's not popular, let's say? Because indeed, we need a more complicated plant, and also in terms of energy consumption, is not a great solution, because we need to heat up the sample to 300 degree or something like this for a given period of time, and this, of course, increases the cost. And so this, but anyway, this is a possibility to apply, another possibility, another way to apply shot peening. Let's go to laser shot peening. This is very interesting. Laser shot peening today is becoming more and more used. Okay. Laser shot peening indeed was defined, invented, let's say, around in 1970 in the US, in that Battelle Memorial Institute in Columbus, in Ohio. And indeed, the production processing, and so the commercial application of laser shot peening are some years later, that is to say at the end of the last century. At that time, the evolution of the laser technology and the laser plant equipment was enough to permit to create also companies dedicated to this plant. And why laser shot peening and not shot peening? Indeed, we will see in the next slide that is more effective. It's able to induce deeper layer of material in terms of residual stresses, and at the same time also a smoother surface. What is the main cons, the main disadvantage is that laser shot peening is much more expensive than traditional shot peening. Okay, so as I said yesterday, I think, or the day before yesterday, indeed, talking with an executive of Airbus, he said, we use laser shot peening, we like it, but we use it when we must use it. Otherwise, we use shot peening because the effects are always good and the cost is much more sustainable. This is the way laser shot peening works. We have a pulsed layer with high energy that strikes against a sample, the part, that is coated by what? By a layer of water, water constraint, okay, and by means of the shock caused by the impact with the sample, by means of this protective water curtain, we have the development of vapor pressure and of a pulsed wave, a shock wave like this. And in this way, this shock wave is very, have a great energy density and is able to induce residual stress after repetitive application. So this is what we see. Here we see a bit better the sample, the material, the laser pulse that is coming from the vertical direction. There is a transparent overlay with the black point, that could be also water, and in the point paint, and then finally by means of this pulsed impact, let's say we have a shock wave that induces residual stresses. Okay. Laser shot peening is can be applied in very accurate part of the component. So is applied typically applying locally and in critical area. You see displayed, and you see the patch is left by the single LSP points. Let's say is applied point by point. We can define a path. Okay, and we must be sure that the path is enough for covering that we are causing some overlap in such a way to avoid that some part of the critical area are not interested by the treatment. Okay, and this is some result in terms of residual stresses, and the one on the left is a qualitative graph, just to give an idea qualitative of the different residual stress that we can obtain by means of laser shot peening. First of all, we will see the first thing that we can see is the different depth of compressive residual stresses. Laser shot peening is more effective, is able to induce much deeper residual stress. And at the same time, also the trend is different. We have a maximum on the surface and then a trend that is continuously decreasing. While for shot peening, we know surface, then we have an increase of compression, and then go down to tensile residual stresses. Here we have another graph. This is more quantitative. This is referred to two materials, and shot peen and the laser peen. The first is the titanium, classical titanium 6 aluminum 4 vanadium alloy. The blue line is shot peening, and the pink line is laser shot peening. And also in this case, what we said, commenting this graph, that the graph on the left can be confirmed. The depth of the treatment is much larger. And even on the surface, the residual stress is a bit larger. And the same conclusion can be obtained with the other material that is used here. And also indeed the trend of the peening and of laser shot peening remained indeed the conclusion, the comment can be the same. The clear difference in of the layer that is covered by compressive residual stresses is also evident, is noted. Okay, here you can see some graph that make possible to understand that also laser shot peening must be correctly designed. Indeed, the final result is a function of the process parameter. In particular, we see here on the left what's happening if you are changing the number of shots of repeated pulsed layer of laser patches, let's say, and the power of the power density of the treatment. And indeed, in the first case with the red line, we have 300 in terms of maximum residual stress compression. In the case of 3 shots and 10 gigawatt over per square centimeter, the effect is much larger. In this other graph, a similar conclusion can be said. The single impact, different energy, and finally, the result in terms of residual stresses is strongly affected by the laser parameter. Okay. This is another image of the blade that we have commented before. Indeed, here is not cannot be recognized the different patches, but anyway, by means of this accurate, fine choice of the part of the component to be peened, we are able to obtain localized effective residual stresses. And here something about the the fatigue strength of the part after laser shot peening. The untreated part is the red line, so it's the lowest SN curve, the fatigue limit around 170 megapascal. The green line is referred to shot peening, and this is effective, of course, more than 200 megapascal. And if we consider laser shot peening, the effect is even larger because we go to 230 megapascal. So in this case, we have 20 megapascal as a difference. Okay, and it's good, it's worth using laser peening. It depends on the application. Maybe if the increment is just 20 megapascal, shot peening can be enough, but it's different, it's larger, laser shot peening could be preferred. This is indeed the qualitative result of the fatigue test conduct use of an aeronautical part, and tensile fatigue, so axial fatigue, cylindrical test bar. The results are referred in terms of spectrum flight hours to failure, and we see here that the improvement induced by shot peening and even more by laser shot peening. So we have that the hours, according to the load spectrum that is defined for assessing the fatigue properties of this part, there is the S-meshing part will fail after something like the 6,000 flying hour. With shot peening, we are going to 7,000, and with laser shot peening, we are even improving around 9,000 spectrum flight hour before failure. Okay, and now let's talk about ultrasonic shot peening. What is this? Indeed, ultrasonic shot peening is close to shot peening. Indeed, we are using again shots. Okay, we are using shot. We are not using laser. This is not a shotless treatment. Okay, but the shot are not the same shot that we are using for shot peening, and also we are using a different equipment. Okay, in this case, what do we need? We need an exciter, an ultrasonic exciter that is a piezoelectric exciter, let's say, that is do this way. Ultrasonic generated transductor that translated the ultrasonic vibration in mechanical vibration, and finally, by means of this sonotrode, we are able to obtain random vibration of the balls that are inside this chamber. Here there is the chamber, you see. We are the ultrasonic signal generator. The vibration is amplified here by means of resonant body, and the high frequency vibration is then transferred by means of the sonotrode, is transferred to the shot, and here is the material to be treated. And by means of this multiple randomic impact of the shot on the part, we obtain something that is similar to shot peening. The shots are different, are generally larger, like these ones. And indeed, by using these different media that you can see here, these are similar to the balls that are used in bearing. We can, and by means of their larger dimension, we can obtain better surface roughness. Okay, and by means, as I said, when I talk about severe shot peening, if we are considering multidirectional and randomic impact, we are going to obtain more easily grain refinement, because the multidirectional impact conditions are making easier grain refinement, ultrafine grain refinement till the nanoscale, let's say, much easily with the twin shot peening. Okay, so it's good, it's bad, it's good, but anyway, also in this case, indeed, imagine here you have a part, for each part with a particular geometry, we must design a chamber that is able to include the detail we want to peen. So it's less flexible than shot peening. We need something that is dedicated to that part, and every time we are changing the geometry of the part to be, or the dimension of the part to be treated, of course we have to change the chamber. Okay, And the same principle can be applied not by considering a closed box chamber and the shot, by considering uh, a pin with a ball at the end that is vibrating. Something what similar to what yesterday we called ultrasonic, okay, shot pinning, that was the same. This was the treatment. So the equipment is the same, okay, ultrasonic generator, vibration, and then, but at the end we have no more the number of shots, but we have a pin or needle that is impacting at high frequency the part, and by moving the pin, we are able to cover the complete the complete surface that we want to pin. And here is some example of pin. In this case, this is more similar to what we commented starting opening the course, that is hammer pinning. This is a sort of ultrasonic hammer that go there, and we can finally treat the part with this tool, and by moving the tool in the appropriate way, maybe with an automatic system. Okay. Okay, and some other detail about ultrasonic shot pinning. The shot material are still being are the one that many times are the ball peeling parts. So are 63 Rockwell C. Can be also ceramic, tungsten carbide, or stainless steel bearing steel. Okay, the other parameter are the mass of the ball in the housing, the total mass of the ball, the vibration amplitude that must be tuned with respect of the application, the treatment times that can vary from some seconds to some minutes, and geometry of the unit. Geometry of the chamber, of course, is important and must be correctly designed. Okay, needle pinning, we need the needle material that is generally stainless steel. The impact radius, that is the impact of the needle that is in touch with the sample, and the number of needle in the chamber that can be one, but can be also, we can have a line more than one needle. Okay, any question? Sorry. I'm talking. Let's see now, before the maybe we can see some image here. We can see a chamber and some application, okay, of this treatment. Okay, what can you see here? Here you see what we are doing, this way to perform on site the treatment. Here there is a manual application of needle pinning by means of this operator. This is the chamber of a treatment, and here is again needle pinning that is applied similarly to deep rolling, hammer pinning, sorry. In this case, indeed, in this case, it's also similar to deep rolling. We have a shaft that is turning, and the hammer here, the pin that is in contact, dynamic contact with the shaft itself. Here is an application that indeed is discovered where everything is done automatically. So there is an operator that is programming the treatment. Okay, so ultrasonic spinning is suitable both for automatic and manual application. The surface finishing, we said, is better than traditional shot pinning. Residual stress field is comparable. No, it's not the same. It's comparable with shot pinning. And grain refinement is easier than shot pinning due, as we said, due to the randomic multidirectional impacts. Any question?
So this warm peening, all other conventional short peening, be it gradient short peening, all other can actually be classified as cold working. cold working process.
Okay. Yeah.
So can this warm peening be classified under hot working process?
It's still cold, indeed. 300, 290 degree is not able to induce phase transformation, let's say. So it's true that it's not room temperature, but we cannot consider it as a hot treatment. It's still considered warm, cold treatment.
In
indeed.
between.
In between, but it's a cold treatment in the end. I would classify, if I have to choose, I would classify this as a cold treatment.
And melting temperature will be.
Yes, it depends. We are quite far, yes. Yeah, yes, we are quite far.
Pasteurization has to be 0.6, so 300 is very.
We are just eating up because something happened, but
Yes.
nothing more. Okay, I think we can. I have around 10 minutes, and then we can stop for the break. Okay, and cavitation peening. This is a shotless treatment. Okay. Here, indeed, from a conceptual point of view, could be somehow compared to laser peening. We have a pulsed wave, but in this case we are not using a laser. We are using water, and in particular we have exploited the phenomenon of cavitation. The cavitation bubbles that, when explode, really leave a lot of energy that impact in the surface, causing this wave that is inducing residual stresses. So this is the way it works. The part is immersed in water. A low pressure vortex is induced by water jet. There is a formation and collapse of vapor bubbles. This is cavitation, okay? And then the collapse transfers the shock wave into the solid surface, inducing, if properly tuned, inducing compressive residual stresses. And this is a representation of the treatment. Indeed, the treatment was developed by Hitoshi Soyama in Japan, and is still the main researchers in this field. Okay, and indeed there are some application where it's very good. And yesterday we were talking about the lattice structure of Fredim, and this could be a treatment that is better adapted than shot peening, because with the shot we cannot reach intricate complex. Could be more feasible to investigate, and the result, and the results are quite good, indeed. Comparing with shot peening, indeed, if you look at the paper published by Hitoshi, by Soyama, indeed, he always said that we are at the same level of shot peening. And sometimes it's true, but what I would like to remark for cavitation is not the level of residual stress that is good, indeed, in the end it's similar, but the possibility then to apply this treatment when shot peening is not suitable, is not a good option for geometrical constraint or for material constraint or for some other reason, let's say. This is a very interesting way to apply shot peening and cavitation peening, and is still under development. Flap peening. Have you heard about flap peening? Flap peening is a niche treatment, let's say, because it's indeed the flap peening treatment was developed in the aeronautics environment, and this is used, and the machine that are used for flap peening are developed and are produced mainly in Canada, in Quebec, where there is a strong aerospace district, let's say. And why I said this is a niche treatment, because it's applied especially to internal surfaces, let's say small holes, where indeed the shot peening and other treatment cannot be effective. While by using this tool, and by imagining we put it in an internal surface of a hole at high speed, by means of this tool that is quite hard with this shot at the end of on the tool itself, we are able to induce suitable shot peening, suitable compressive residual stresses. Okay, so the shots are bonded to a flap here, the tool, what I call the tool here. These are the shots. Okay, and everything is put on a rotating mandrel. So this is turning at high velocity. Okay, the flap was, the treatment was created to cover small reworked area of the part that has been pinned, indeed. And today it is also used for life extension, to repair and for life extension. After a part has been used for a number of cycles, a number of time, or a number of hours, let's say, or years, we use flap pinning to make it usable again. Okay. And pre-stressing the part enhances the ability to form part by P, it's okay, but here what maybe is more important is this key. Here we have the flap, the yellow part, and at the end we have the hard balls that are the tool of the treatment. Okay. The shot is tungsten carbide, ceramic. So here is an application on a small hole, you see, that must be pin or repair, let's say. The tungsten carbide avoid any possible contamination for non-ferrous alloys. Shot is contained and so can work on assembly structure with relative ease. So we have not, the shot remain as they are. We are not going everywhere, like it happened with shot pinning. Minimal removal of finishing on completed part with localized protection. If everything around is protected, we don't need any post-processing, let's say. Saving, it's quite cheap, let's say. And it's used for parts that are difficult to be reached with other treatment. Here, indeed, here you can see the relation between the traditional Hellman intensity and the Hellman intensity measurement done with flap pinning. Okay, why? Because with flap pinning, we are not using the screw, but we are using a magnetic cord to prevent the damage of the flaps. If you are using the screw to fix the Hellman strip, the flap could be damaged by the contact with the screw. So screw are avoided. It's used this holder that is magnetic, and this means that the final measurement of the archive will be different with respect of the traditional one. And so this is a scale for converting the Hellman A intensity to the 3M, that is this device, or older intensity. Here is some result about fatigue residual stresses. Okay, and the comparison is again with conventional shot pinning. And indeed, what can we say that also in this case, the final compressive residual stresses are similar to what we can obtain by means of shot pinning. And also, indeed, the fatigue curve here is quite qualitative, let's say, and it shows that if with rotopinning, we are able to get a bit better fatigue strength. But it depends on the application, the way it is done, and so on. This is clearly published by someone using flap pinning. Okay, and here the test specimen in this case was this, with this groove that was treated by means of flap pinning at the groove. And finally, deep rolling. Deep rolling is not a pinning process, of course. Deep rolling is a contact and mechanical treatment. based, of course, on contact of the tool of the roll. But in this case, we have not an impact. The contact is continuous, and the treatment is this. We are using a tool, a roll, or a sphere, and we press it on the part to be treated in such a way that we are inducing plastic deformation and finally residual stresses. The advantage of this treatment is the ability to obtain good surface roughness and deep residual stresses. We can also use what is called today also surface burnishing. That is, we are using this tool, this sphere, instead of a roll, and in this way we are able to induce plastic deformation if we are applying a suitable axial load, contact load, let's say. This is burnishing, and is suitable for metal parts, even hard, such as hardened steel and so on. These are some applications, some example of application, the way it can be applied. Deep rolling can be applied. This is hydrostatic, or with a mechanical single roller or multiple roller like this. And all by means of hydrostatic tools that to induce the load. Here is an example of burnishing, some example of burnishing. In this way, by burnishing, we are able to treat also not easy surfaces, such as grooves, cylinder, and thread, and so on. And the applications are quite wide. Indeed, a classical application of rolling is the crankshaft for cars or for other reciprocal engines, and medical technology and so on. The thread are generally used are deep rolled if we want to obtain good fatigue strength and so on. Here, indeed, we have already commented this graph that now is completed, and these are the part that we said we are deep rolling the smooth and the notched part, and we see that by considering the optimal condition for deep rolling, we are able to induce an improvement of the fatigue strength, and the improvement is much more remarkable if you are considering the notched part. And now we know why. We have discussed many times why, and which are the parameters that are important for a correct design of deep rolling: the load, the contact load, and the number of passes of the load, the number of time we are reading the contact of the tool of the roller with the part. Okay, we have at the conclusion now. What can we say? In general, the peening processes present an effective way to improve the mechanical behavior of structural element. Today, the application of such as all of them, let's also consider for in view of the making more sustainable production, we are trying to extend the design life component and of the system. And this kind of is good for direction to life, for extending a single part, also structural repair. And finally, indeed, I did not, we have introduced the machine learning, let's say more in general, the I4 concept, and this will, the application of this concept to these peening processes will make even more effective what the result we are able to get by their application. Okay.